So this is just a little work on the problem 34A off a study guide. And what we want to consider when we're asked to simplify something like this is that we've got two different things going on. We are simplifying some variables that are under the radical sign and a number that's under the radical sign. And although the same principles apply to both, we kind of do some different things to simplify numbers and to simplify variables. So let me focus on just the 350, and then we'll focus on the b to the 7th and the d to the 8th. So the first thing that I think we should note is that this problem up here is the exact same thing as the square root of 350 times the square root of b to the 7th times the square root of d to the 8th. So it's totally acceptable when the items underneath the square root symbol, so I suppose I would say when the 350 here and the b to the 7th and the d to the 8th, when they're all being multiplied together under a radical, or when anything's being multiplied together under a radical, you can separate them out. That does not change the value of the expression whatsoever. So now that I've separated this out, let's consider just for a moment, how am I going to deal with the square root of 350? Well, anytime that I want to find the square root of a number, I first want to ask myself, is that number a perfect square? For example, I know the square root of 36 is 6 because 6 times 6 is 36, right? And so it's a perfect square. That makes it easy. But 350 is not a perfect square. There's no number times itself equals 350. And that number, or the answer, if you were to plug this into a calculator, would be irrational, right? It would be an irrational number times itself. So no whole number times itself equals 350. So what we want to do is we want to pull out as many perfect squares as we can find in the number 350. So we want to find the factors of 350 to do that. So I like to set up a factor tree. And finding the prime factorization of 350 really is the way to go. So right off the bat, I'm going to notice that 50 times 7 is going to be 350, I think, because 7 times 5 is 35. So 50 is 2 times 25, and then 25 is 5 times 5. So if you remember way back from prime factorization, learned in maybe 6th grade, 5th grade, once we find the prime factorization of a number, all those prime factors times each other equals that number. So 7 times 2 times 5 all should equal 350. That's the whole point of the factor tree. And you could test it on a calculator. Here we get 14 times 5, which is 70, and then 70 times 5, which is 350. So I'm going to change just this part here on the left to be the square root of 2. I'm just going to put the numbers in order. Times 5 squared, because there's 2 5s, times 7. And now I'm going to kind of clear my workspace here. So I've got that factor tree. Now I know, okay, the square root of 350 is equivalent to what I've just written here. 2 times 5 squared times 7. Well, I only see one perfect square out of all this stuff. 2 is not a perfect square. I can't think of anything that times itself is going to equal 2. 7 is not a perfect square. No whole number times itself equals 7. But 5 squared, or 5 times 5, is 25. So there's definitely a perfect square here, and that is 5. So what is the square root? If I asked in a separate question, what is the square root up here on the upper right-hand side of the screen? What is the square root of 5? You'd say, well, that's 5. And so that's all I'm going to say. I'm going to essentially pull that out. So I'm going to say, okay, that's equal to 5. Let me change colors here. 5 times the square root of 2 times 7. I could not pull out the 2. I could not pull out the 7 because the square root of 2 is irrational. The square root of 7 is irrational. But by golly, the square root of 5 squared I can pull out because that's just 5. And here's a trick to know. Anytime the number here, you know how there's like an invisible 2 here? Anytime that number 2, or whatever number is here, matches as the exponent of something, you can pull one whole thing out. And that goes back to this idea that the square root of x squared is just x. Because the 2 here and the 2 here, let me do a pointer. Because this 2 and this 2 match, it just becomes x. Because the square root symbol asks what times itself equals what's underneath me. And x squared is just x times x. So of course the answer there is x. So this simplifies down further to 5 times the square root of 14. Okay? So we have now taken care of the 350 portion. I'm going to cross that out. But now we still have to address the b to the 7th and the d to the 8th. I'm going to go to the next slide to do that because I've kind of run out of room. So we've already determined that the square root of 350 is equal to, if I remember correctly, 5 times the square root of 14. So now we need to figure out, because remember we split this up into the square root of 350 times the square root of b to the 7th times the square root of d to the 8th. So let's take a look now at the square root of b to the 7th. So I'm going to split this up just like I did the 350, but I'm not going to need to do a factor tree to do it. Okay, so I'm going to say that the square root, and I'm going to come down here in the color blue, I'm going to say that the square root of b to the 7th is the exact same thing as the square root of b squared times b squared times b squared times b. And the reason I'm saying that is b squared, this one, times this one, times this one, times a single b is equal to b to the 7th. So I haven't changed anything, I've just changed the way it looks. And again, anytime the exponent matches the number of the root, so this is the square root, you just end up with the base. So, or in this case, you would just end up with the b. Because the square root of 1b squared is just b. Because what times itself is b squared? B is. So I'm going to be able to pull out 1, 2, 3 b's. So I'm going to have b to the 3rd out here, but I've still got 1b stuck inside. So now I'm going to say, okay, b to the square root of b to the 7th is now equal to b to the 3rd times the square root of b. And here's the trick for that. Anytime you've got, and so I'll come up here to this part right here, anytime you've got that number there, right, this is the square root, so there's a 2, you can kind of take the exponent, 7, and divide it by that number. So that's, 7 divided by 2, and you can ask yourself, how many holes can you get out of that? Well, 7 divided by 2, that's going to get me 3 holes, right? So I could pull out 3 b's, but there's still 1 left over. And that remaining b stays underneath the radical sign. And d to the 8th, I'll do that one quickly. D to the 8th, if I divide that by the 2, I know that 4 2's fit in 8, right? So I'm going to be able to pull out 4 d's. So this is just equal to d to the 4th. And that makes sense. This is asking what times itself equals d to the 8th? Well, I know from past work with exponents and power properties that d to the 4th times d to the 4th equals d to the 8th. Because when the bases are the same, you just add the exponents. So this is making a lot of sense now. So my final answer to this problem is going to be 5 square roots of 14 for the number. And then I have to add in the what I got for b to the 7th and what I got for d to the 8th. So let's write the final answer on the next slide. So my final answer for this is going to be what I could pull out for the 350, which if I remember right was 5. What I could pull out for the b's, which if I remember right was b to the 3rd. Then I know I could pull out 4 d's. But then I have to multiply that by whatever was left under the radical sign. And I remember the number 14 was left because we had 5 times 7 from the 350, and there was 1b left. So this is my final simplified answer to that problem. Okay, on the next slide, I've realized that doing all these problems would create a grossly long video, so I'm going to just do a few of them, and I'm going to try to choose ones that I think would be the most helpful. Okay, so this problem, I believe, is 34C. I better write that down, 34C. Okay, so this is the cubic root, excuse me. So we've got this 3 here, which is important because that's asking what times itself is underneath me. Or, for example, a times a times a is a cubed, right? And so the cubic root of a cubed is just a. Okay? So knowing that, how can we evaluate this nasty looking fraction? Well, as it turns out, everything on this fraction is a perfect cube, which is really nice. So the cubic root of 64, I think, is 4, because 4 times 4 is 16, and 16 times 4 is 64. But before we leap there, let's look at a property that lets us approach this problem. This whole thing is equal to the cubic root of 64 divided by the cubic root of 27 k to the 6th. And the reason we're allowed to split that is because, well, it is a property, but there's a reason it works. And instead of elaborating right now, let me just show you the process of this problem, and then maybe I can address why. And in case you forgot, the property that we learned about in class was something like this. And this works for any sort of root. And we went into it in class, why does that work? Why is that true? And I can do that here in a few minutes. But let's continue with the problem, assuming that that is understood. So, there's perfect cubic roots here. So the numerator just becomes obviously 4, right? Because 4 times 4 times 4 is 64. And that just leaves us with this denominator to worry about. Well, I know the cubic root of 27 is 3, because 3 times 3 is 9, and times 3 is 27. So that's easy. We got rid of the 27. But k to the 6th. So what's the cubic root of k to the 6th? Whoops, k to the 6th. Well, remember, we can divide this number here by this number, and that kind of helps us figure out how many we can pull out. But this is also a pretty basic problem if you think about it, because the cubic root of k to the 6th has to be k squared, because k squared times k squared times k squared equals k to the 6th. And so the way I did that, though, so quickly is I said, hey, what's 6 divided by 3? Oh, it's 2. So I have 2 sets of k to the 3rd I can pull out. Because this right here, the cubic root of k to the 6th, is the same thing as the cubic root of k to the 3rd times k to the 3rd. And so each one of those k to the 3rds, they cancel each other out. And so it's just k squared here in the denominator. So 4 over 3k squared would be our answer to that problem. Okay, multiplication actually is nice because it's what I think the easiest out of all the properties because it's the most intuitive. So whenever you have a situation like this, what you do is you multiply the numbers underneath the radical and you multiply the numbers outside. Again, we talked about why that worked in class, and I'm going to assume for right now, just because we're down to the wire, that the why behind that's understood. And so now we're just working on the fluency or the process of the skill. So we get 6 square roots of whatever 7 times 14 is. And I better be sure I get that right. So 98, square root 98. So 6 square roots of 98. But it may not be simplified all the way. Let's check 98. Well, let's do a prime factor. Find the prime factorization of 98. We obviously know that 7 and 14 are factors. But 14 is 2 and 7. So what becomes really interesting here is this is 6 square roots of 2 times 7 squared. So because it's the square root of 2 times 7 squared, that's the same thing as 6 times the square root of 2 times the square root of 7 squared, and the square root of 7 squared is just 7. So that's the same thing as 6 times 7 times the square root of 2, which is 42 square roots of 2. All right, on the next slide, let's talk briefly about the multiplication of radicals and that last property we used in the problem with the fraction. Let's discuss the why behind those two things. That's what I'll do on the next slide. So the first why we wanted to consider is if you have like a root, and it doesn't really matter, the nth root. It doesn't matter if there's a 2 there, a 3 there, a 4 there. This works for anything. That's equal to the nth root, and n's just a variable showing any number can be there, over the nth root of b. Whoops, messed that up. Let me fix this real quick. There we go. Okay, so why does that work? Well, that's actually a really good question. And I'm not going to give you like a proof of this, but let's just quickly look at some numbers. So if I asked you what's the square root of 2/3, or not 2/3, let's go with, let me find a better example here. I have to think for a second. Let's go 4/9. What I'm asking you is what times itself is 4/9? And you could think right in your head, oh, that's 2/3. That's obviously 2/3, right? Because 2 times 2 is 4 and 3 times 3 is 9. And so therefore 2/3 squared, or 2/3 times 2/3 is 4/9. And what's interesting is when you ask yourself, if you look at the whole thing as the fraction it is, and it's an easy fraction like this, you actually end up with another fraction that is the root of the numerator over the root of the denominator. So what's the square root of 4? Well, that's 2. And what's the square root of 9? Well, that's 3. And so that's just one example of why this works. So it's working with easy numbers, and it consistently works with easy numbers. So I'm going to assume it works with numbers that aren't necessarily so easy to wrap my mind around. And that is just a real quick why behind it. Not a formal proof, but just a demonstration with numbers. Let's look at that other property we wanted to discuss. Not necessarily property, but why when you're multiplying radicals, can you just multiply what's underneath the radical? So let's talk about what we know about a radical. So we know a radical is the same thing as whatever's under it to the 1/2 power, right? So for example, let's go to a different color. The square root of x is x to the 1/2 power. So the properties of exponents that we learned also apply to radicals. So with that in mind, if we're multiplying, for example, the square root of 2 times the square root of, 4, we know that's going to be equal to the square root of 8. So what allows us to multiply the 2 and the 4 and keep it under the radical? Well, let's rewrite that. This is the same thing as 2 to the 1/2 power times 4 to the 1/2 power. And what's interesting about that is this is the same thing, okay, what I just wrote here in white, is the same thing as 2 times 4 all to the 1/2 power. Because if you remember, we learned that a to the r power all to the s is a to the r times s. And we extrapolated that further to say, okay, a times b to the s power is the same thing as a to the s times b to the s power. So this little exponent outside gets put to each term, and we went over why that works. Well, this is the same thing. Now I'm going to take the 1/2 power and apply it to both. But so it's just this property in reverse. That's what allows us to combine the 2 and the 4 under the root. Because, hey, 2 times 4 to the 1/2 power is the same thing as 8 to the 1/2 power, which is the same thing as the square root of 8. So that's a quick, brief explanation. Let me do a few more, and I hope this is helping. Okay, so I hope I'm not confusing anyone further by going into such detail. Sometimes I go into too much detail and make it hard to follow. So I apologize if I'm doing that. I would be happy just to sit here and do all the problems for you, and you could watch me do them, but that would be kind of lame, right? Well, not that this is any less lame. So let's look at 34i, right? 3 square roots of 3 over square root of 7. The idea is, what are we to do with this? Well, we don't want to leave the denominator an irrational number. The square root of 7 is irrational. So let's rationalize it. The way to do that is to multiply the numerator and denominator by the square root of 7. That is going to result in 7 in the denominator because, in case you've forgotten, man, my pen is doing weird things. Let me fix this. Okay. Let's get it on track here. Because the square root of, x times the square root of x is just x. That's the same thing as saying, hey, x to the 1/2 power times x to the 1/2 power is x to the 1/2 plus 1/2, because remember we add the exponents, which is x to the first. So again, going back to all of our radicals are affected by our exponential properties because they're the same thing. And so we know from past learning that this in the numerator would be 3 square roots of 21. We just multiplied the 3 and the 7. And the 3 on the outside stayed on the outside. So we have to ask ourselves, is this as simplified as we can possibly make it? Well, the only way that we could simplify further is if we could pull something out of the 21. So let's think about the prime factorization of 21 real quick before we make judgments on whether or not we're done. 21 is 3 times 7. Well, they're both primes. There's not a single one that repeated, so nothing can be pulled out. This would be my final answer to 34i. Okay, so I think the last one I want to do in this is 34j. And for all my subscribers, and you're wondering, what in the world are you doing, Mr. Prashar? Why are you just randomly showing problems? It's because I've had some requests for help on this problem. And so this is not your typical instructional video. This is meant to answer a very specific request. So, okay, this problem, 4 square roots of 3 times the square root of 6 plus 2 square roots of 3. Okay. So there's really two ways we could approach this problem. We could look to see if we could add anything in the parentheses and then multiply, or we could just begin with distribution. If I look straight at this, I know 6 right here, that's 2 times 3, so I'm not going to be able to pull anything out to make this like terms. So I'm going to begin with distribution. In other words, I'm going to multiply the 4 square roots of 3 times the square root of 6, and then add that to whatever I get when I multiply 4 square roots of 3 times 2 square roots of 3. So remember, when we're multiplying, we multiply what's under the radicals and what's outside the radicals. There's nothing outside the square root of 6 except for 1. So I'm going to keep the 4, but that's going to become square root of 18 plus 4 times 2 is 8. So the outside numbers got me the 8, and the inside numbers are going to get me 9. Now I just need to look at this. Okay, before I do anything, I notice straight away that this 9 is a perfect square. So that makes life nice and easy. So this is 4 square roots of 18 plus 8 times 3, because the square root of 9 is 3, or 4 square roots of 18 plus 24. But now I need to look real close at the 18. I want to make sure I can't simplify that any further. So let's find the prime factorization of 18. 2 and 9. And then 9 into 3 and 3. So this is the same thing as 4 square roots of 2 times 3 squared plus 24. So I can pull out 1 3. This 3 right here, because it matches that little number, right? So this is going to become 4 times 3 square roots of 2 plus 24, or my final answer of 12 square roots of 2 plus 24. And there's one little thing that I think is important for you to know if you're struggling with these, that really this problem didn't answer or didn't demonstrate very well. So I'm going to make one up really fast on the next slide. I'm going to call that the end of this video. But real quick, let's summarize this. This on the outside here, 4 times 3, that's what got me the 12. The 24 again came from the 8 times square root of 9. So I distributed, did all these steps, and ended up right here at my final answer. The thing that this did not demonstrate very nicely is when can you add or subtract roots. And so let me talk about that really quick on the next slide. Okay, so when can we add or subtract roots? We'll treat them just like variables. For example, if I asked you to simplify the following expression, x plus 2 minus 3 plus x squared plus 2x. What I would expect you to do is combine like terms. So in red here I've got all my x's. In blue I've got my x squared, and then underlined here I've got just, the normal numbers. So I would combine my terms. I would have 3x, I'd have -1, I'd have x squared, and I'd rearrange those, of course, to be something like this. And we all know that. So why am I showing you that? Well, because you kind of do the same thing with radicals. So if I've got 3 square roots of 2 plus 4 square roots of 2, that's the same thing as simply saying I've got now 7 square roots of 2. Because I had 3, I had 4, now I have 7 of those things. Same with subtraction. If I had 3 square roots of 2 minus 4 square roots of 2, that's the same thing as saying, okay, now I have -1 square root of 2. And so you really treat them like variables, but here's where things get tricky. What if I said, hey, 3 square roots of 2 plus the square root of 8. You might say, well, there's no like terms. I can't combine the square root of 8 and the square root of 2. Well, you'd be right, except for the fact that the square root of 8 simplifies down. So before you make any judgments on whether or not something can be added or subtracted, simplify everything as far as you can. So let me erase some of this above, and I'll show you what I mean by that. So again, we're going to find the prime factorization of 8 and make sure it can't be simplified. If it can, we're going to simplify it and see if what's left under the radical allows us to add or subtract. So 8, I know that's 2 and 4, and then 4 is 2 and 2. So this is the same thing as 3 square roots of 2. By the way, all this was an example before. It has nothing to do with what I'm doing now. So 3 square roots of 2 plus the square root of 2 cubed, because there's 3 2's, right? And that is the same thing as 3 square roots of 2 plus 2 square roots of 2. Because I know that the square root of 2 to the third, again, is the same thing as the square root of 2 squared times 2. And so that 2 squared cancels itself out, so I pull it out, and I'm still left with the 2 under the roadway. So now I've got a final answer of 5 square roots of 2. Okay, I hope this video was helpful for you. I will shoot you the link, all the students who have requested 34. And good luck to you guys. I am 100% convinced you guys are going to rock the finals. So I don't want you feeling discouraged. And please keep coming with the email questions if you have them.